Good day, ladies and gentlemen, and welcome to today's presentation, What's New in StatXact and LogXact 11. My name is Tyler. I'll be in the background answering any WebEx technical questions. If you do experience difficulties using your WebEx session, you can contact me in the Q&A panel. It's on the lower right side of your screen. I'll do my best to assist you. For all other technical issues, please call WebEx support. Their number is 866-779-3239. Please note that as an attendee, you are part of a larger audience. However, due to privacy concerns, the attendee list will not be displayed. All attendees are in listen-only mode and will remain so during the duration of the presentation. And as a reminder, this webinar is being recorded. We will be fielding questions throughout the duration of the presentation today. You may ask an online question at any time by simply entering your question to the Q&A panel, again on the lower right-hand side of your screen, and clicking Send. Please leave the Send to defaulted as all panelists. With that, we invite you to sit back, relax, and enjoy the presentation. I would now like to introduce your speaker for today, Chris Corcoran. Chris, you have the floor.
Thank you, Tyler. Thank you very much. I appreciate your help with the technical support. I'd also like to thank Mike Whites at Cytel, who's also standing by and who has offered some technical support. As Tyler said, my name is Chris Corcoran. I'm a professor in the Department of Mathematics and Statistics at Utah State University. And I have a long connection with Cytel. I've worked with Cyrus Mehta, Proles, and Chowdhury on many research projects over the years, some of which have culminated in additional functions and modules that have been added to StatXact. So I've worked with StatXact fairly extensively for a long time, since my own time in Boston working with the folks at Cytel. In fact, I'd like to just pause and acknowledge some of my collaborators at Cytel, including Hrishikesh Kulkarni, and of course Pralay, whom I've worked with for a long time, and A.R. Kanaphan, who have worked extensively on the new versions of StatXact and LogXact, and I'm not, unfortunately, able to include the names of many others who work behind the scenes, many programmers and others who have tested and documented the software. I'd also like to acknowledge the founders of Cytel Software Corporation, Cyrus Mehta and Nitin Patel as well, who started with what I'm showing you on the following slide. This is an early version of StatXact, and I'm amused by looking at this slide every so often and remembering how it is that we used to store and load our software. I don't know if you remember, if anybody on this call actually remembers floppy disks, but there you go. Starting out with Cytel version 1 and moving forward to the present version 11, the underlying rationale for StatXact and LogXact has always been to fill a gap that was recognized by Drs. Mehta and Patel back in the 80s, which is that large sample methods often just fail altogether or work not very well or very unreliable for categorical data where the samples are small or sparse. So that's always been a driving force behind StatXact and LogXact, is to provide tools that allow for accurate, robust analysis of samples for which large sample methods just don't work that well. Of course, there's a balance, because the sorts of procedures that are found in StatXact and LogXact for so-called exact inference are also very computationally intensive, and so it takes a lot of research and development on the computational side, the algorithm side, as well, in order to make these functions practical for the sorts of data sets that researchers want to analyze from day to day. But with some very humble beginnings, I think just to give you a brief roadmap, when those floppy disks were the source of distribution for StatXact software, this is what StatXact began with: exact tests of trend for 2x-C tables, tests for 2x2 tables, including stratified tables when comparing two proportions, and also say Fisher's exact test and the exact chi-square test and others when you have unordered R by C tables. So from that beginning, going from version 1 to 11, now this is a sampling of many of the menu items that are found in StatXact, and so the functionality is increased in extraordinary ways. In fact, if you look at the menu items here on the right of this slide that are currently found in StatXact version 11, you notice that these arrows here indicate additional submenus that allow for a wide variety of functions. I think too many for me to count, with a myriad of options as well. In addition to other capabilities, including charts and plots and data management functions that I haven't included the menus for here, but that's where StatXact is now, a Windows-based menu-driven program that includes a large variety of tests for categorical data, but also for continuous data. So it's grown quite a bit. The reason I share that with you at the beginning is that I think it's important to understand what drives additions and improvements over time when it comes to StatXact and LogXact. I mean, part of those improvements you could classify as the provision of additional statistical functions, so increased functionality, and also improving the properties of the tools that are made available in StatXact, the statistical properties. In addition to that, there's the need to improve, there's the ever-present need to improve computing efficiency. As I said, these exact tests are computationally very challenging. And so over time, as memory has increased in modern computing environments, even as we've moved ahead now to things like cloud computing and the capability to do parallel processing and so forth, these tools are leveraged by StatXact in ways that allow users to carry out analyses much faster than they could, maybe 20, 25 years ago when StatXact first began. So computational developments are also very important. Now, in terms of version 11, just to provide somewhat of a roadmap regarding how these improvements for version 11 fit into those different categories, these are some of the primary enhancements or improvements that I'm going to review today with some examples. For example, just some options that improve the performance of exact tests, and by performance I mean statistically, the statistical performance of exact tests. A Bayesian approach that's been added now, new tools for regression, including a bias reduction tool that I'll be illustrating later, and also the ability for researchers now to carry out a negative binomial regression within LogXact, and also a new toolkit that includes tests for genetic association. On the other side, there's been an attempt to improve the computing power of StatXact and LogXact, one by allowing for parallel processing, and another that allows users to define R functions that can be included in their StatXact session. Now, of course, R and R functions have really grown in importance in modern statistical research, and this capability now gives users much greater flexibility in defining their own test statistics, for example, that they can evaluate within the StatXact environment. So, in other words, it allows them to define their own test statistics, but use the powerful computational engines within StatXact to evaluate the performance of their test statistics. So these are some of the new enhancements that we're going to review here briefly this morning. But I kind of want to take a step back to just illustrate very briefly why these issues are important when considering these improvements to StatXact. Of course, just very broadly speaking, not to oversimplify, but just to speak very generally, the advantage of exact tests the general advantages are that they're much more accurate and useful for smaller, sparse samples. In other words, there are times when for small samples or very sparse samples, large sample methods just fail altogether. And exact tests are exact in the sense that they guarantee a type 1 error rate that's set a priori by the analyst. So if you decide that your significance level is 5%, using an exact test guarantees that you don't exceed that. In many settings for finite samples, there's no such guarantee for asymptotic or large sample methods, like, for example, just the conventional chi-square test or others like it. On the other hand, exact tests can be challenging, and these challenges are the types of problems that Drs. Mehta and Patel and Perlace and Chowdhury and others at Cytel have tried to address over the years. One challenge is that when you actually use a type 1 error rate, exact tests sometimes tend to be conservative, and I'll illustrate what that means here in just a moment. And as I've said before, the other challenge is that exact tests often are computationally more challenging. And so even though they're more robust and they guarantee the type 1 error rate, they take a little more time and a little more memory. So just as an example, suppose that this is the outcome of a hypothetical clinical trial. Of course, I don't think anybody would be interested in a clinical trial with 8 subjects, but this is just to illustrate the points on the previous slide. Here we have for treatment, we observe 3 responses out of 4, whereas for control only 1 response. And the question would be, for an investigator, is there some sort of treatment effect? In other words, is this evidence that the 75% response rate among those who are treated is significantly higher than the 25% response rate under those who are in the control group? And so using conventional statistical practice, we would ask, well, what's the probability of this result? And what's the probability that we would see something as or more extreme than this outcome under the hypothesis that there's no treatment effect? Well, without going into too much detail, these probabilities can be computed using a simple hypergeometric distribution if we assume, for the sake of argument, that there is no treatment effect. If there's no treatment effect, then these same 4 individuals would have responded regardless of which group they were in, treatment or control. And so it's very straightforward to compute what we would call an exact probability for each of the tables that one can imagine would be observed under these experimental conditions. That's here on the next slide. These 5 tables represent the 5 possible outcomes of this experiment, given that the null hypothesis is true. In other words, we have 4 people in each treatment arm and 4 that would respond. And each one has some probability associated with it. The reason why the last 2 are in red is that they represent the observed table, and also a table that represents kind of a more extreme outcome than the one that we observed. That's where we have 100% response in the treatment group and 0% in the control group. And so to compute an exact p-value, we simply add up the probabilities of those tables at or beyond the observed table. And in this case, that probability is 0.243. And I don't think that any of us would decide that that constitutes evidence of a treatment effect. But nevertheless, for illustrative purposes, suppose that as a researcher, I decide that I want a type 1 error rate, or I want to use a significance level of 5%. Well, then we would find evidence of a treatment effect were I to observe 100% response, a 100% response rate in the treatment group, but not for the observed table. In other words, the 24.3% is greater than 5%, so I would say that there's no evidence of a difference. But if I had observed 4 responses in the treatment group and 0 in the control group, then I would declare that to be significant at the 5% level. But the consequence of that is that the actual type 1 error rate is the probability that I observe 4 responses, which is 0.014, which is less than 0.05. For this reason, that's why these sorts of exact methods are sometimes referred to as categorical, or I'm sorry, as conservative, in the sense that the actual type 1 error rate, because of the discreteness of the distribution of the data, because there are only a finite number of p-values we can observe, the actual type 1 error rate is going to be less than, generally, the nominal type 1 error rate that I've set in advance. And then it's worth pointing out that the other thing that is happening here is that in order to compute this exact p-value to begin with, I need to keep track of all the tables in the reference set. So those 5 tables for that experiment I just described, I need to somehow store those in memory if I'm going to compute the p-value. Now for this example, that's not very challenging, but for a moderately large data set, the number of tables in that reference set grows exponentially larger, and so it becomes a much more difficult problem. So this example is just kind of used to illustrate those 2 issues, the tendency of exact methods sometimes to be a little more conservative, and also the need to store the tables in that kind of reference set in order to compute the exact p-value. In other words, the computational challenge that comes with that. So again, the advantages are we guarantee that the type 1 error rate is preserved for an exact method, and exact methods hence are more robust, or even sometimes represent the only option in some cases when the asymptotic approach doesn't work. But on the other hand, we have this conservatism and we have the computational challenge that we need to solve. So, in other words, the reason I've reviewed this just briefly is to give you some idea behind the rationale that leads to enhancements and improvements in StatXact and LogXact, or how those improvements have been added over the years. For example, to combat conservatism, versions of StatXact later than version 1, subsequent versions of StatXact over the years have included a lot of well-known strategies that reduce that kind of conservatism. In other words, that allow you to have the guarantee of an exact method that you're preserving the type 1 error rate, but that improve the statistical power. In other words, the actual type 1 error rate is closer to the one that you set in advance. These are just some examples, and I don't want to spend any time on these, but these just represent kind of a subset of additional methods over the years that have been included in among the StatXact, within the StatXact toolkit that help to alleviate that conservatism. So when you're analyzing data, there's always a balance. I mean, you want to control the type 1 error rate. You want to have statistical power that's as large as you can, where, again, statistical power represents the probability that you detect some sort of effect when, in fact, that effect exists. So you want high statistical power, and you also want fast computation. You don't want to wait for days and days to get your results. So there's a balance between these three objectives for any data analysis, but certainly that balance is something that Cytel has focused on as StatXact and LogXact have been developed over the years. So while this is broadly true, specifically for StatXact, what that means is that over the years there's been an attempt to refine exact tests to improve power. And by refine, I mean using exact distributions that are maybe not quite as discrete so that users have an actual type 1 error rate that's closer to the one that's set in advance, like say 0.05. What that does is it helps to improve statistical power. So it allows you to control for type 1 error by making sure that you have power that's as high as you possibly can achieve. Second is that because exact tests are so computationally difficult, of course, another big objective within Cytel over the years has been to make sure that the algorithms that yield exact results, both in StatXact and LogXact, are as efficient as they can possibly be. And finally, there have been a lot of procedures added over the years that I guess, for lack of a better term, I would refer to as near exact procedures. In other words, they're not exact in the sense that they preserve the type 1 error rate, but they perform a lot better than asymptotic methods at a much lower computational cost. So they're trying to, they're included to allow users some options when perhaps they have a data set for which exact methods don't work quite as well, or they're not hard, they're not easy to compute because of the size of the data set. But at the same time, these near exact methods allow users some options that provide good properties, good balance between type 1 error and power, without requiring all the computation of exact methods. So let's go back and review some of those procedures, some of those enhancements that have been included then in version 11. So I've already listed some of these on a previous slide, but under the category of reducing conservatism for exact methods, so exact methods that are a little more refined, one of the additions to StatXact 11 is the use or the availability of Blaker's method. This is based on a paper that was published by Dr. Blaker back in 2000. The reference is available in the StatXact user manual, or you can ask me for it if you'd like. But this was a method that was proposed that can be broadly applied to many exact inference problems. And so in StatXact, it's been applied to, problems of one proportion Poisson rate or stratified Poisson rates, or two related proportions or two independent proportions with or without stratification. So it has the advantage of being somewhat broadly applicable as a strategy. And what it does is it helps to refine the exact distribution in a way that allows that actual type 1 error rate to be closer to the nominal type 1 error rate. So that improves power. And I'll show you an example of that in just a moment. Under the heading, or I guess under the category of near exact methods, there have been a couple of things added to StatXact and LogXact to the toolkits in both those packages that allow decent performance for small or moderately large samples at a much lower computational cost. So these aren't necessarily exact in the sense that they're guaranteed to preserve the type 1 error rate, but they perform well, and they're included to improve, I guess, increase the flexibility that researchers have when they're analyzing data in StatXact. So in StatXact, a whole cadre of Bayesian methods have been included for comparing two proportions. Those allow investigators to compute, confidence intervals and to do inference for odds ratios, as well as risk difference and relative risk for two proportions. Which is very useful because I'll talk about this more in just a moment, but inference for the risk difference and the relative risk is only possible in an unconditional analysis, which is much more computationally difficult. So this provides an additional tool in the kit that allows investigators, if they are looking at the risk difference or the relative risk, an option if the exact version is very computationally hard. In LogXact, in this category, there's been a new option added for bias reduction for logistic Poisson negative binomial regression models. And this is important in cases where for finite samples, the maximum likelihood estimator just doesn't work very well. And so I'll illustrate that here in a moment as well. But let's start with Blaker's method. Now, we don't have time in this webinar to go into, theoretical details about how some of these work, but the reason why I used that kind of hypothetical clinical trial example earlier was so that you could at least get the gist of what Blaker's method is trying to accomplish. Blaker's method is basically refining that exact distribution in the tails to allow for a more powerful approach. In other words, what Blaker's method does is it's an exact method, but it allows you to achieve a type 1 error rate, an actual type 1 error rate that's closer to the one that you set in advance. It does this by considering a two-sided p-value when you're computing an exact test that is comprised of the minimum one-sided probability, so it looks in the tail in the observed direction, plus it uses probability in the opposite tail that's as close as possible to that one-tailed probability. And again, what this accomplishes is it allows you to work with a more refined reference set that improves statistical power. It reduces the discreteness of the exact distribution. And as I said before, another advantage of this is it's very broadly applicable. It can be applied to one proportion, one Poisson rate, including stratified rates, related proportions to independent proportions. And so, it has kind of a broad impact, this option, across many different procedures that are already available in StatXact. So, for example, a professor surveyed 28 students, and 0 of those students reported being a practicing vegan. The question is, what can we conclude about the proportion of vegans in the underlying sampling population of these students? Well, as you can see, because 0 self-reported being a practicing vegan, that makes it impossible to use any kind of asymptotic inference. In other words, the observed proportion plus or minus some number of standard errors, because the standard error in this case is going to be undefined as well with 0 successes. And so we have to use some sort of exact method, and the common method is to just use the binomial distribution, do a test based on that binomial distribution, and obtain a confidence interval by inverting that binomial test. That has a name. It's called the Klopper-Pearson interval, but there have been many improvements on that over the years, including this Blaker's method. So I'm going to go to StatXact here. And it's very easy to input these data. I just want 1 row and 2 columns. So we're just talking about a single binomial proportion. Here, these will be my non-vegans. And in the other column, these represent my vegans. There were 28 who were non-vegans, and so 100% of my sample was non-vegan. And so the question is, what proportion of my sample of the underlying sampling population is vegan? How do we do inference for that? Well, for one sample rates or proportions, we're talking about a single binomial. And notice here, this Blythe-Still-Castella, this is an option that's been in StatXact for a while, but it accomplishes the same thing in principle as what we're trying to do with Blaker's method. So I do want to compute that as well. It helps to refine the exact distribution to give me a little more power. But here now is an option for Blaker's method as well. Now, when I choose that option here in this window, notice it says use Blaker's method wherever applicable. For any procedure in StatXact for which Blaker's method can be used, now, until I uncheck this box, Blaker's method will be applied as well. And so when I hit OK, you can see that I get some confidence intervals on the proportion. Here, this is a confidence interval on the number of vegans. And so you can see that, the confidence interval is 0 to about 12.3%. This is the standard Klopfer-Pearson interval for using the exact binomial distribution. But you can see that the Blythe, Still, Castella, and Blaker's method intervals are a little bit narrower. Now again, you might recall from Statistics 101 that all things being equal, as long as you're preserving the confidence level, it's better to have a narrower interval. In other words, we have the same certainty on a smaller interval. So that's very useful. And that's exactly what these two alternative methods are trying to achieve, is they're building on the advantages of exact methods, but improving their power. So when you use Blaker's method, the bottom line is that you're getting a slightly more powerful exact approach. And this is evidenced by the fact that the interval here, 0 to about 11.4%, is shorter than the standard binomial approach. So what about the Bayesian approach? Now this is not an exact approach, but it's near exact in the sense that its properties for finite samples seem to be fairly decent. And so just to provide another option to researchers now, Cytel has included a Bayesian approach for comparing two proportions in StatXact. Now, again, in 1 hour or less, I can't go much into depth when it comes to Bayesian methods in general, or the specific Bayesian methodology that's underlying these two proportion comparisons. But the upshot is that what we're doing with the Bayesian approach is we're treating the two proportions as random variables that come from their own distributions. These distributions we call prior distributions, and then inference for the difference between the proportions relies on what's called the posterior distribution, which is the prior updated by the observed data. And again, it's not exact, but it's computationally a lot cheaper. And the other big advantage is that, as I said before, it's something that can be used to do inference for the risk difference, the difference between two proportions, and the relative risk, or in other words, the ratio of proportions. Now, the odds ratio, exact inference for the odds ratio is typically performed conditionally, and so it's computationally a little easier than exact inference for a risk difference or a risk ratio. And so the fact that the Bayesian approach can be applied to these kinds of unconditional metrics, the risk difference and the risk ratio, is another advantage, because it can be, computed for most problems very quickly. So as an illustration, a data set that's actually included in the StatXact installation under the datas file is a study of lymphoma and occupational exposure to this phenoxy acid. So in other words, prior exposure and whether you eventually were diagnosed with lymphoma. And the scientific question is there an association between exposure and subsequent lymphoma risk? Again, going back to StatXact here. I've already uploaded this data set. Here's what it looks like. You can see that of the cases, 16 were not exposed and 8 were exposed to this phenoxy acid, whereas out of the controls, 44 of 53 were unexposed. And so the question is, does this indicate some association between prior exposure and your risk of lymphoma? So going to the menu to compare two proportions, two independent binomials, You can use the Bayesian approach for several of these procedures. I think, especially down below here, the test of superiority, the test of non-inferiority equivalence, superiority, and so on. So I'm not going to run through all of these, but let's just focus on the difference in proportions. Or actually, I'm sorry, let's focus on the odds ratio. I mean, this is a case control study, so it would make the most sense. Now notice that now here's an extra option that's available in StatXact 11. You have the option of doing the asymptotic inference or the exact for the odds ratio or the Bayesian. So here I'll choose exact. This provides a point estimate of the odds ratio, which is 2.4. So in other words, the odds of lymphoma for those who are exposed are about 2.4 times the odds for those who are unexposed. And here's the exact p-value and the confidence limits on the odds ratio. So it doesn't appear here as though there's any significant difference in lymphoma risk based on exposure. Now going back and choosing the Bayesian option. Now you can see that you are likewise given a couple of estimates. One is the mode based on the posterior distribution. The other is the median of the posterior distribution. The 95% confidence limits are also obtained from the posterior distribution. But one thing I want to point out here, and again, we can't provide a lot of details in a brief webinar like this, but I want to point out that the selection of the prior distributions for each of the proportions is somewhat critical, and that is an issue. The prior distribution you can see here that's being used for the proportions is a beta, which is sensible because the beta distribution in this case is what we call a conjugate prior, in the sense that if you use a beta distribution for the prior, then you also have a beta distribution for the posterior. But the question is, how do you select these parameter values from these individual beta distributions? If you're really interested in that question, there are some good discussions out there, including one that I think is a good, brief, very concise and practical discussion by Alan Agresti in his book, the third edition of Categorical Data Analysis. He has a couple of pages there on the use of Bayesian methods for comparing two proportions. One of the things that he points out is that sometimes for smaller samples, the results can be somewhat sensitive to the choice of these priors, and so you have to perhaps do a little bit of a sensitivity analysis. But nevertheless, there are different choices for these parameters. Of course, here by default, we're using parameters of 1 and 1 for these beta distributions. You could also use a uniform prior, which is that the b equal to 0 in both cases. So-called Jeffreys prior, a and b are equal to a half, and so on. But there's more detail provided in the user manual, as well as again in a few textbooks, including Alan Agresti's textbook. So let's talk about the bias reduction methods in logistic regression that are available now as well. Again, this doesn't represent an exact method, but it's a big improvement on, in a lot of cases, on the maximum likelihood estimator. Now, all of the computational problems for exact inference are multiplied when you carry out an exact regression. Exact regressions are very computationally difficult. And so improving the performance of regression methods for finite samples is a big goal of LogXact in particular. But the problem is that it's been well understood for a long time that maximum likelihood estimators result in some well-known bias for finite samples. And in some cases, the MLEs may not even exist in cases where samples are small or sparse. And where exact options are useful, they're robust and they work even where the MLE doesn't, they're computationally more challenging. So I guess you'd say one potential compromise is this bias correction method that's received a lot of attention over the last several years and is being used more and more, that appears to correct this bias for finite samples and do so in a way that allows, given that you have this bias correction tool, you can perhaps make your estimators a little more robust without the computational challenges in some cases of exact methods. The first correction is fairly computationally simpler than exact for sure. And so the upshot is that it kind of provides an intermediate alternative. So where the sample size may not be large enough for asymptotics to work very well, but is too large for the exact to work very well, or the nature of the covariates makes exact challenging, then this bias correction method can be useful. For example, this data set having to do with remission rates of leukemia patients, this data set has been included with LogXact. There are two covariates. One is what's referred to as the percent labeling index, and then the highest recorded patient temperature. So investigators were interested in the associations between these two variables and how these patients experience remission. So just to show you very quickly where that's found here in StatXact, here's the data set. These are the 27 patients with their status representing whether or not they experienced remission, and these two variables of interest that we want to use to analyze remission rates. So under regression, I can accomplish this either by using logistic or probit regression, but I'm going to go with logistic. I specify my response. I have my covariates here. And notice that down below I have options including asymptotic, exact, Monte Carlo. I'm going to go ahead and run the asymptotic here. This just carries out a standard maximum likelihood analysis. And we can see the values of the regression coefficients, the resulting inference. It appears that temperature has very little to do with this, but the Li variable seems to be significantly associated with indexing. But I just want to demonstrate how the bias reduction method can be selected. So again, going to binary response, logistic model. I have the same model, but under options, this penalized MLE for bias correction or first method is what we've been talking about here. I select that. Go ahead and run it. You can see it takes very little time. It's not that computationally difficult. But in comparison to the asymptotic approach, just the straight MLE, here you can see that the betas are somewhat smaller than what we observed for logistic regression, 3.3 and about -50 versus about 2.6 and about -35. Substantively speaking, the inference is a little bit is the same, but this difference in the parameter estimates for this regression model using the bias correction reflect the typical result when you apply this method. In other words, MLEs often the bias is in the direction of the alternative. So MLEs for finite samples tend to overestimate the actual effect sizes. And so this kind of reduced beta represents some correction of that to some degree by the Firth method. Hey, now those prior improvements I've talked about have to do with providing options that either improve existing exact methods or provide robust kind of near exact properties at a lower computational cost. But there have been some tools added to the kit that just represent brand new functions that are now available in StatXact. One of those is that in LogXact. One of those in LogXact is negative binomial regression, which is useful for modeling counts, but particularly in cases where you have Poisson data that has extra variability. Also, this was included on the list of topics that we would cover, but the genetic data tools are something that are fairly involved in terms of their scope and their illustration. And so we may be doing a future webinar where we illustrate how these genetic tools work. We don't really have time in today's session to review them too much, but it's kind of an exciting new addition to StatXact because beyond just genetics data, these new tools allow for multiple testing. It's a huge problem in genetics where you have many different markers that are being tested for association simultaneously. And so multiple testing problems arise in those settings. And so we are excited for these tools because it provides a permutation-based approach that's a lot more robust, especially when many of these tests within a given data set involve sparse data. But as I said, it's something that we're probably going to have to focus on for another webinar in the future. But I would here like to just briefly illustrate how the negative binomial regression works. If you'll recall, again, from your prior statistics training, if it's been a while since you thought about the negative binomial, a negative binomial variable is a count, just like a binomial or just like a Poisson, but it represents the number of trials required for a fixed number of successes. But where it's used in a lot of practical settings is in cases where you have a Poisson count, but you have a lot of extra variability that a negative binomial model helps you to absorb. Remember that a Poisson distribution assumes that the mean and variance of counts are equal. But in practice, that assumption is violated quite often. So in other words, a regression model for both a Poisson and a negative binomial look very similar, that you're talking about the log average count as a function of perhaps several factors of interest. But in a negative binomial model, unlike a Poisson, there's an additional parameter that represents this extra variability, or also this is also referred to sometimes as over-dispersion. And so it allows you to get much more reasonable estimates of effects and standard errors in particular in cases where that extra variability exists. So as an example, these survey data come from 1,308 subjects. And these subjects were asked, within the last 12 months, how many people have you known personally who were victims of homicide? And the data here in this table are summarized by race. So notice there are, about 150 who were classified as black, about somewhere around 1,100 or 1,200 who were classified as white. But over to the right side of this table, I've also included the average and the variance of these counts. So these data, just for the sake of compactness, are displayed here in group form. In other words, there were 1,070 whites who said they had never known, they haven't known one person in the past 12 months who were murdered, 60 who had known one, and so on. But when we average over all of these counts across these subjects, you can see that the average number of homicide victims reported by blacks is almost 5 times higher than that of whites. But the other thing I want you to notice is that the variances here are much larger than the means. So in other words, even though these are technically, these can be considered to be Poisson counts, the variability is much higher than we'd expect if these counts actually followed a Poisson distribution. I mean, for blacks, the variance of these counts is more than twice as large as the average, and for whites, it's, you know, in that same ballpark. So that would be a concern. So going to LogXact, just here briefly. Again, these data are my own. I haven't. They're not my own. They actually belong to Ellen and Grusty, but I've entered them myself here. If you're interested in this file, you could probably get it from one of our colleagues at Cytel. But here are the data, and under the regression menu, I can go to count data. I can either model these as Poisson counts or negative binomial. So for Poisson, the count is the number of victims. The covariate of interest here is race. I go ahead and run the analysis. Okay, I don't want to look at this quite yet. I want to do this again with negative binomials. So again, here we have the same outcome. The count is the number of victims. The covariate is race. Okay. Go ahead and fit this model as well. Now, what I want you to notice is that the beta corresponding to race, in other words, the coefficient of race is exactly the same in both cases. It's 1.733. But for the negative binomial model, the standard error is substantially higher. It's about 0.24 as opposed to about 0.15 for the Poisson. Now, this reflects the fact that the extra variability is absorbed by this negative binomial model in a way that it's not within the Poisson model. Another indication of this is that this ancillary term in the negative binomial model represents this kind of over-dispersion or extra variability term. The null hypothesis is that this is equal to 0, and you can see that this ancillary term has a value that's close to 5 with a standard error of 1. So in other words, there's very strong evidence here of extra variability or over-dispersion. So the negative binomial model is much more appropriate in this case. So now that that's been included in the LogXact package, that gives investigators kind of one extra piece of flexibility. And I should also note that the first correction that we talked about earlier is also available for this negative binomial model. Well, just to close, under the category of faster and more flexible computation, there are a couple of major things I think that have been added to version 11. One is parallel processing capability, and this is especially useful. It's been applied to several unconditional procedures that, as I said before, are very computationally intensive. So to be able to compute these procedures in parallel is very useful where parallel processing is available. The other is that the other enhancement, as I mentioned before, is that R functions can now be used in the StatXact environment. Just as an example, I'll go through this quickly so that we have some time here at the end. But the upshot is that a user can define their own test statistic within an external function, R function, and call that function within the StatXact environment to use StatXact's computational engines to evaluate that test statistic. So here's some smoking data that are provided with the installation in the data set of files, the data file folder in the StatXact install. But the question here is how your smoking status is associated with the years that you've had the habit. The power divergence test statistic is something that's not included in StatXact, but can be programmed in R and read from an external file. So from the menu, you would just need to go under non-parametrics, user-defined tests using R. You can fill in this menu according to instructions that are given in the user manual, but it allows you to name the test, to identify the file where the test is contained, the R functions, to identify asymptotic or exact functions within that file that you're reading in, and then when you hit OK, you're given results for your own test statistic that you've defined. So instead of having to run your own Monte Carlo simulation, which for somebody maybe coding this up themselves may be very inefficient, you can use StatXact's more efficient routines to get a faster Monte Carlo sample. The only other thing I want to mention that we haven't reviewed here is that in the last version there was a whole module that allows now for the analysis of correlated categorical data. I'm bringing down the menu here to show you that there are lots of tests here for correlated categorical data. This wasn't something that we had time to go over today, but there have been, for two-ordered multinomials with correlated data, there have been some additional capabilities added that allow you to kind of define the nature of the correlation structure within your data set. So that's another kind of enhancement that's been included for that major new module. And that's all. I'll leave it there and wait for your questions.
Hi, this is Mike Weiss of Cytel here in Cambridge, and we'll be now moving and transitioning into a live Q&A session with Chris, and we invite you to post your questions, and we'll select as many as we have time for, but we're happy to go past the top of the hour to address your questions. I did want to remind everybody that StatXact 11 and LogXact 11 are now available for installation, and those of you with you can find out more about that simply by going either to the StatXact or LogXact pages and simply click on the sales button you'll see on the right, and you can find out more about pricing and your license options. I'd also like to remind everyone that you can see, for those of you making the trip out to JSM in Seattle this year in August, you can see more and get further demonstrations on both StatXact and LogXact, and I believe Chris is making the trip out this year, as well as many folks on Cytel in the software development team. So you have a chance to get demonstrations from some of the people actually behind the software. So with that now, I also want to remind people that the slides for today's webinar are available directly from our homepage. They can be downloaded by anyone, and everybody who registered within 1 to 2 business days. So usually by Monday, you can expect an email with a link to the replay as well as the slides. We're going to get into some questions now, but we're going to start with a question that has been posed by others as we began demonstrating StatXact and LogXact 11. And Chris, maybe you could tell us a little about, you showed us, you spent some time on the new Bayesian-based method tests. One question we had often was, what are the choices for specifying the prior distribution in those Bayesian tests?
Right. I think that during the presentation I showed you the beta distribution. The beta is available as a prior, and as I said, the beta is really useful because it represents a conjugate prior, so it yields the same posterior as the same distribution for the posterior as you used for the prior. So that makes it somewhat convenient. On the other hand, there is one other option besides beta distributions where you specify your own beta parameters. The other option right now is that you use just the percentiles of both of the proportions. So the distributions of the proportions that you're trying to compare, you specify the percentiles directly. But those are the options right now, either a beta with any parameter values that you specify yourself, or using the percentiles of those distributions directly.
Thanks, Chris. And another question we had posed to us is a lot of folks are now taking advantage of StatXact and LogXact's R integration capabilities. Maybe you can talk a little bit more about the R integration in StatXact 11 and what really sets that apart from previous versions.
I think that the thing that's really advantageous to me is that, I'm kind of an academic statistician. I work at a university, and a lot of my colleagues do as well. And R has really become, something that's used in a standard way in academics for testing out new methods or new modeling approaches or new statistical techniques. It's an extremely flexible environment because you can program most any method of interest, and you can also make those functions available to other researchers through the use of R packages and so on. So the problem, of course, with R functions and sharing R functions is that for very computationally difficult problems, often, as statisticians, we're good at statistics, but we're not that great at programming. And so our R functions perhaps aren't all that efficient, especially when you're talking about permutation-based inference. And so what StatXact is allowing people to do now is to say, okay, well, I've got my own function, I've got my own statistic that I want to evaluate, but I don't want to reinvent the wheel in terms of computing an exact distribution or taking a Monte Carlo sample from scratch, because that's something that StatXact does very well. And so StatXact now allows users to, kind of define their own test statistic function and then, kind of take it for a ride, I guess, using the very efficient algorithms that exist in StatXact. I think that's kind of what StatXact is going for, is they're allowing users that kind of flexibility while using what StatXact does really well.
Thanks, Chris. And this might be a time to talk and mention a little bit about the prox versions of StatXact and LogXact. Of course, those are the versions that offer StatXact and LogXact all their tests and procedures and all the features directly within the SAS environment, within the SAS's own menu structure. Maybe you could talk a little bit about that.
Yeah, you bet. I think for several versions of StatXact now, I can't remember dating back to which one, but for a while now, with new releases of StatXact, there have been companion parallel releases of proc StatXact and proc LogXact, which basically contain all of the procedures available in StatXact, but as you say, in a kind of an environment that's completely compatible with SAS. So in other words, you can draw on the efficient computational engines of StatXact by just using the the programming commands that are specific to proc LogXact. So in other words, all the procedures available in StatXact and LogXact can be accessed in SAS using some command structure that's been specified by Cytel and is all documented. But again, it just increases your flexibility in allowing you to kind of draw on those things that StatXact and LogXact do very well, but do it within a SAS environment if you're, if there are other complementary analyses or exploratory analyses that you're also carrying out in SAS. I think, Mike, you can probably speak to when those procs will be available for this version. I'm not totally sure about that. I'm thinking it's within the next 2-3 months or something. I could be wrong.
Yeah, that's correct, Chris. The prox versions of both StatXact and LogXact are in the final development and testing stages right now, and they should be released in 2 3 months at the most. And again, we'll let all the registered users know about that, and you can always visit Cytel.com and the StatXact and LogXact pages for updates on availability. But yeah, people can rest assured that they will be available sometime this summer. And again, you can see the prox versions in action at JSM, or simply go to, again, Cytel.com StatXact or LogXact pages, click the sales request button, and our people will be able to put together a demonstration for you as well. Chris, did you have any final thoughts before we wrap up today?
Do you mind if I answer a question that was just submitted by Nathan Pace?
Oh, good. Absolutely. Good to see the question.
Nathan is asking how many random effects can be used in correlated tests. Can these, can the structure be nested or crossed? That's a good question, Nathan. The suite of correlated data tests that we have currently in StatXact, I guess the first point I'd make is with respect to how they compare or correspond to, say, using a random effects approach. In a random effects approach, of course, you kind of absorb some of that, within group or within cluster correlation with that variance component. For the exact test, what you're doing is you're using an exponential family model that conditions out the correlation between subjects, and so you achieve an exact test while still accounting for the correlation, but you don't actually estimate the degree of correlation. Now, I think it's possible using the approach that we have to maybe include kind of a nested effect as well, to have 2 levels of correlation. That's not something we've added yet to StatXact directly, but we do allow for correlated data tests with stratified data. So in other words, you could use stratification to add 1 extra level of correlation, so to speak, or account for that extra level of correlation if you have, that kind of nested structure. If you're kind of interested in that, I'd be happy to talk about it. You can just email me directly, and and I'd love to chat kind of offline. And also, Mike, just very quickly, and I'm sure probably there are a few people who feel that way. Somebody asked, we didn't really get a chance to cover the genetics at all. I think our plan is to run a webinar in the future, perhaps even the near future, I'm not sure, but something that talks specifically about genetics. I mean, that's something that would take some time to illustrate and explain. But I will say that that if you're familiar with genome-wide analyses, you probably know that one of the biggest software packages out there that's used by people, analyzing genetic data is Plink. And Plink has some permutation-based multiple testing procedures, but they take an inordinate amount of time to run. And what we've implemented are, again, building on what StatXact has done well over the years, which is exact tests very efficiently. We've kind of leveraged that for genetic analyses by improving that permutation-based approach, so that we've actually made, using parallel processes and some better algorithms, we're making these kinds of permutation-based multiple testing procedures available for a larger number of data sets and a larger number of settings. So I will say that. I'm sorry, I know that's not adequate, but that's something I'm sure we'll be working on soon, is trying to give people a chance to hear more about that.
Thanks, Chris. And we just want to remind folks, we're still with us. You'll see Chris's email there and Prale's, but maybe for users who have questions, maybe the best path to answering questions is simply support@Cytel.com for users of LogXact or StatXact. That's always a way to get into the experts here at Cytel. We welcome you to engage with Chris, but some of your answers about the use of the software may be best answered by the team here. Chris, we were also we've had some questions earlier about and pointed people back to the manual for examples and whatnot, and without actually spending a lot of time, but on specifics, but maybe as a close, you could show folks how to access the online help and the tutorial examples in either StatXact or LogXact. Thanks.
You bet. Let me go there. And while I'm bringing this up, let me say also that somebody piped in about the multiple testing procedure for genome-wide studies. Is it controlling the so-called family-wise error rate or the false discovery rate? And it's the former, just so you know. The permutation-based procedures are the kind of the resampling procedures referred to as the min-p and the max-t. But let me go back to Cytel Studio. Under Help, Online User Manual, you can go to any one of these manuals. For example, if I wanted to learn more about Blaker's method, any of these new methods are mentioned in the preface, and more information is given there. But here, notice that in the preface, at the very beginning, some of these things I've talked about are discussed in the preface as enhancements to version 11. But Blaker's method is discussed in these chapters here. So if you wanted to know a little more about Blaker's method and how to apply it to actual data sets, for example, here's how to apply Blaker's method when you're looking at stratified Poisson samples and so on. So that's the way to access the user manual. And of course, it's possible also to as Mike said, to just contact user support directly. I've found that Cytel is very prompt in their responses to those who have questions about how to use certain procedures. They have a good support team. So don't hesitate to use that option also.
Great. Thanks, Chris. And I'm going to thank everyone who attended today for their attention and continuing interest in Cytel's exact statistics packages, StatXact and LogXact. We take a great deal of pride here at Cytel with our exact software and its continued development. It really, in many ways, was the beginning of Cytel and continues to be an important area of research and development for the company and the people here and our statistical researchers and our software developers. And we're very, very grateful to have someone like Chris to be able to help to explain and to communicate the usefulness and the applications of the new features in the software, the methods and tests and procedures that are contained within StatXact and LogXact. So with that today, I want to thank once again everyone, remind them that you can download the slides from today's session directly from the homepage on Cytel.com, and that everyone will receive via email links to the replay. And we, of course, encourage you to share the slides and the replay with your colleagues and are ready to take your questions at support@Cytel.com about the use of the software. Your options for licensing and pricing can be easily answered from going to the LogXact or StatXact pages on Cytel.com and simply press the sales inquiry button there. All right. Once again, thanks to Professor Chris Corcoran at the Utah State. This is Mike Weitz from Cambridge, and we're signing off for today. Everyone have a good day.
Ladies and gentlemen, that does conclude today's presentation. You may now disconnect.